let's review the microreaction and see how it can be applied to synthetic problems. The microreaction involves alpha beta unsaturated carbonyls as substrates, and when a carbonyl is conjugated with another pi bond, it extends the resonance that's available to the system. So we know that all carbonyls have resonance. We could have an O- and a C+. But when we have a second site of unsaturation between the alpha and beta carbons, the resulting carbocation in that drawing is allylic, and so we can move the positive charge down to the bottom carbon. So overall, we see that when we think about the reactivity of an alpha beta unsaturated carbonyl, we notice that the carbonyl carbon, as always, is partially positive, but the beta carbon as well is partially positive. So when a nucleophile is approaching an alpha beta unsaturated system, it has a choice whether it's going to attack the carbonyl or it's going to attack the beta carbon. And in fact, most nucleophiles prefer to attack the beta carbon. That's described as conjugate addition or 1,4 addition. So when a nucleophile attacks the carbonyl, we describe it as 1,2 addition. In other words, it reacts just like an ordinary carbonyl. Nucleophiles that prefer to add at this position are things like Grignard reagents or hydride. They're described as hard nucleophiles. And soft nucleophiles, things that are more stabilized, for example, an enolate prefers to add at the beta carbon, we call that 1,4 addition or conjugate addition. And the nucleophile we're going to be most interested in using for this reaction is something like an enolate nucleophile. That's what we describe as the microreaction. So just a quick example of what this would look like if we have a cyclohexenone here. If we react with a Grignard reagent, that Grignard reagent is going to attack at the carbonyl as usual. And after aqueous workup, we will get the alcohol. So it typically behaves like an ordinary ketone, even though it is conjugated, where if we use a cuprate instead, the cuprate is going to prefer the conjugate addition, has a different reactivity than the Grignard, and so it's going to attack the beta carbon. Now, what happens when I attack the beta carbon? I could do that because I could push the extra electron density up onto the oxygen atom. That's a good place for the negative charge to go. Okay, and now when we think about that second step, when we do our workup, where am I going to protonate this intermediate? If you look closely, you'll note that this intermediate is an enolate, and enolates do not ordinarily react at the oxygen. They react at the alpha carbon. So it is the alpha carbon that's going to get protonated in our second step, and we're going to get our ketone back. So actually, when you do a conjugate addition, the two groups that end up getting added across the pi bond is we get a nucleophile added to the beta carbon, and we get a proton added to the alpha carbon. So it appears, when you look at the product, it appears as if the carbonyl remains unchanged. It remains unchanged and appears it's not involved in the mechanism, but in fact it's critical for the mechanism. Without that oxygen there, you couldn't have addition to the alkene. This is not an ordinary alkene. It's an electrophilic alkene. We describe it as a Michael acceptor because it could accept this conjugate addition. Just for comparison, let's take a quick look on what it would look like if we protonated at the oxygen instead. Just a little reminder of why that would not look right. When we take a look at that product, that is the enol, and enols are unstable. This would spontaneously tautomerize back this way to the ketone. So even if you made the mistake of accidentally protonating at the oxygen, you should recognize this product as an unstable product and draw the ketone version instead. But actually, looking at this product, it makes a little more sense of why this mechanism is sometimes described as 1,4 addition, because when you look at it this way, you could see that the two groups, the nucleophile and the proton, are added 1, 2, 3, 4 to each other. So that's what our conjugate addition, that's where we get our terminology. Okay, so let's take a look at what the Michael reaction looks like. The Michael reaction, it's going to be an enolate that attacks the carbonyl. And it's usually a stabilized enolate. I'm going to show an example where it's just an ordinary enolate. But let's see if we could predict the product here of what we're going to get. Our nucleophile is going to be the alpha carbon. And you know what, let's just go ahead and add a second group here to make it a little more realistic example. So the alpha carbon here is going to be our nucleophile. It's the beta carbon of the enone. That's going to be our electrophile. So that's the bond we're going to form. And the product we're going to get is going to have new carbon-carbon bond formed at that beta position. And we'll have our enolate group adding in that position. So this typically is a stabilized enolate. In other words, the Michael addition usually involves an enolate that has two electron withdrawing groups. So for example, this ketoester having two carbonyls here. So what does that mechanism look like? The mechanism begins with a deprotonation at the alpha position. So we have a base here, and I'm sorry, let's use, because I used an ethyl ester, let's use sodium methoxide here, so we don't have any hydrolysis potential. So I'm going to deprotonate to make the enolate as step 1. And after making my nucleophile, this is now going to undergo the Michael addition, or the conjugate addition. Again, it's the alpha carbon that's going to react, and the beta carbon, that's the bond we're forming. And so we attack and push the electrons all the way up here. And I think this is kind of the #1 place where students make mistakes and lose some carbons. So take note here that we have 1, 2, 3 carbons in this example. So we want to make sure we still have those 3 carbons when we draw our next intermediate. So this is the carbon we attack. That's our new carbon-carbon bond. And then we have the CH2. And then we have O minus and H. 1, 2, 3. So we're going to get an enolate intermediate. If we did the Michael addition correctly, we'll have an enolate intermediate. And then that's going to be protonated in our second step. Protonated in our last step. We could use the ethanol protic solvent. To get our Michael addition. So again, focusing in on our new carbon-carbon bond. And there's the 1, 2, 3 carbons that we added on to our enolate. Okay, and when we look at this product, we see that our product has the pattern of a 1,5 dicarbonyl. So this is another pattern we can look for when we do a disconnection, when we're exploring our target molecule. If we see a 1,5 dicarbonyl, that's going to give us a hint to what kind of disconnection we can make. Let's see if we can do that here. Okay, so here we have a target molecule that has that exact pattern. If we take a look at the relationship of these two carbonyls, 1, 2, 3, 4, 5. So the 1,5 dicarbonyl relates to the disconnection of the Michael reaction. And as usual, I'm going to focus on the alpha carbon. And really, you could look at either alpha carbon, carbon 2 or carbon 4. They're both alpha carbons. But this is going to be the better disconnection in this case because I have 2 electron withdrawing groups here. So that's going to be the better nucleophile. So that's where my disconnection is going to be. The alpha carbon was my nucleophile. And so this is the carbon that was my electrophile. So let's take a step back and look at our synthons. We have an enolate as a nucleophile, and this is a reasonable nucleophile, especially because it's a stabilized enolate. It has some extra resonance stabilization with both carbonyls. But the electrophile that I want needs to be electrophilic in a position that is beta to a carbonyl. Okay, so how do we do that? We accomplish that. What is the reagent that has that reactivity? We accomplish that by adding a double bond between the alpha and beta positions, right? That makes the beta carbon electrophilic. Now you might think, well, why don't I just attach a leaving group there? Because I've done that before to make a carbon nucleophilic, a carbon electrophilic, put on a leaving group. You know, would that be an okay approach? But that is not going to work, because when you have a beta leaving group that is very unstable and will very easily eliminate HCl, we'll eliminate that leaving group to give the double bond instead. Okay, so what we want to look for as our two components are going to be the enolate as our nucleophile and an alpha beta unsaturated system as our electrophile. So our synthesis, after we've done our planning with the retrosynthesis, our synthesis is going to be combining our alpha beta unsaturated with our ketoester with some base, and we'll get our target molecule. So the synthesis in these reactions is usually quite straightforward. It's the retrosynthesis, the planning, that is the more challenging part.